So class, we talked briefly about glucose and the various configurations, the alpha and beta anomer of glucose. One more sugar that is utilized a lot in our studies of carbohydrates. They're all used a lot, but one of them that probably you're familiar with besides glucose is fructose. So just as before as in glucose, we have fructose, but it is also a 6-carbon sugar. Okay, so just like glucose, fructose has 6 carbons, and we will depict these carbohydrates in 2 forms. One is the Fischer projection, and the other one is the Haworth projection. We tend not to use the chair conformation for cyclohexanes because the substituents get a little bit tedious to draw. So let us draw the Fischer projection of fructose. It is a 6-carbon sugar, and it has this structure, 6 carbons, so there's a lot of similarities between fructose and glucose. Let's first depict the formula of fructose. So we have 6 carbons, carbon number 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So this is C6. How many oxygens do we have? 1, 2, 3, 4, 5, 6. C6O6. And how many hydrogens do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 hydrogens. Well, C6O6H12 is also the formula for what other sugar? Okay. Well, you guessed it, glucose. Okay. That's another C6 sugar. So fructose and glucose are isomers. Okay, but that's it, really. They are isomers of one another, and that is as far as we can go. Remember, in isomers, we can have enantiomers, we can have epimers that differ in 1 chiral carbon, where all the other chiral carbons in the molecule are the same configuration. So that's about it in terms of similarities between glucose and fructose. Just as glucose and fructose are both hexoses, C6s, we will call fructose as a ketose because this is a ketone functional group. So this is a ketose. It's a sugar that has a ketone, so we'll call that a ketose, and also we can call this a hexose. So you'll have pentose sugars and hexose sugars. Those are the most common ones that are found in the body. So this Fischer projection, the open chain form, is really not how fructose, a 6-carbon sugar, would want to be in its most stable state. Just as before, fructose will undergo a nucleophilic attack. So a lot of common themes here: an intramolecular nucleophilic attack, which leads to an intramolecular cyclization. Cyclization, which is the common form of these molecules. They like to form a ring structure, and the molecule that forms the ring is or initiates the nucleophilic attack will be a chiral carbon that's farthest away from the anomeric carbon. So what is the anomeric carbon? All right, so in glucose you found the anomeric carbon to be C1, right? So remember our definition of an anomeric carbon. It is a carbon that is not chiral but suddenly becomes chiral as a result of an intramolecular nucleophilic attack. All right, so what carbon does the nucleophilic attack? It's the same one as before, it's carbon number 5, and this will do an intramolecular nucleophilic attack on this carbon, and that pair of electrons goes to the oxygen, and that pair of electrons that goes to an oxygen actually picks up a proton. So what you get after this intramolecular nucleophilic attack is what is known as a hemi-ketyl intermediate. This is akin to a hemiacetyl intermediate when glucose undergoes a nucleophilic attack from within. So here are our 6 carbons. And here is our hemi-ketyl intermediate. So here we have a hemi-ketyl intermediate. Much analogous to the hemiacetyl intermediate that we found when glucose undergoes an intramolecular cyclization. So this hemi-ketyl intermediate, actually, we can put it into the Haworth projection. So this is what it would look like in the Haworth projection. Coming back to fructose here, all right, on the Fischer projection, if your substituent on the chiral carbon is facing the left-hand side, that is up in the Haworth projection. If the substituent on the Fischer projection is facing the right-hand side, that is down in the Haworth projection. Okay, HP stands for Haworth projection. Let's take an assessment of our chiral carbons. We have a chiral carbon here. I'll put that by an asterisk. I'll have a chiral carbon here, that's carbon number 4. Carbon number 5 is a chiral carbon. Carbon number 2, okay, carbon number 2 is going to be not chiral, but once it undergoes nucleophilic attack and picks up that proton, the orientation of the resultant OH can be up or down on the plane. So once this undergoes the nucleophilic attack and this hemi-ketyl intermediate forms a ring, okay, we will have a carbon atom that it suddenly becomes chiral. So this is the anomeric carbon. Okay, so the anomeric carbon for ketoses such as fructose is going to be carbon number 2. And that will be the anomeric carbon for all ketoses. Okay. So you can have an alpha or beta anomer at fructose, and that alpha or beta comes from carbon number 2. And likewise, when we compare it to glucose, all aldoses, the anomeric carbon will be carbon number 1. So glucose and other aldehyde sugars, which we call aldehyde sugars, aldoses, we call all ketone sugars ketoses. So what will this look like in the Haworth projection? Our Fischer projection into the much more adaptable and much more used in the literature, the Haworth projection. So let's take a look at this again. We have a CH2OH, that's not chiral. This is the anomeric carbon. This is chiral, this is chiral, this is chiral, this is not chiral. So what is going to make up our ring? Our ring is going to be made up of carbon 2, 3, 4, and 5, but then that oxygen is also going to get in there. All right. So we actually have a 4-carbon ring, and that 5th atom is going to be an oxygen. Okay, so 4 carbons and an oxygen. So let's first go with carbon number 1, but realizing what makes up our ring is 2, 3, 4, and 5. Okay, so actually we'll start off with the oxygen that's going to form part of our ring. So we'll do that. What's attached to this oxygen? All right, we have the anomeric carbon. It's carbon 1. I'm sorry, carbon 2, right? The oxygen from the anomeric carbon, or the anomeric oxygen, is attached to carbon 2. What is attached to carbon 1? Okay, what is attached is a CH2OH. What is attached to carbon 2, the anomeric carbon, CH2OH? Well, we already wrote that. And then we have our third carbon, carbon number 3. It's carbon 1. And then our fourth carbon, carbon number 4. Carbon number 5. And what is attached to carbon number 5? Okay, that's the carbon that has the hydroxyl group that forms a nucleophilic attack. So that is going to complete our ring, carbon number 5 with carbon number 2. All right, so 3, 4, and 5. And what is attached to carbon number 5 is the CH2OH. And that will be carbon number 6. Okay. So let's put the OH substituents. All right, in carbon number 2, the anomeric carbon, the OH can be up or down, above or below the plane of the ring. So if it's below the plane of the ring, it's the alpha anomer. If it's above the plane of the ring, it's the beta anomer. Okay, so this OH can be above or below. If we put it below, I've given you the alpha anomer of fructose. Okay, this only occurs in the anomeric carbon. Okay, because remember, when this forms an OH, that OH can be above or below the plane of the Haworth projection ring. Carbon number 3, the OH is on the left-hand side, so that means up in the Haworth projection. Carbon number 4, the OH is on the right-hand side. That means down in the Haworth projection. Carbon number 5, the OH is on the right. So that means down in the Haworth projection. Okay, so carbon number 4, it's on the right. Carbon number 5, it's on the right. And that means both of them, the OH substituent is down. All right. So that is alpha fructose. The alpha is based upon the OH on the anomeric carbon. And will this fructose be in the D or L configuration? We look at the carbon that's farthest away from the anomeric carbon. That also is chiral. So the carbon that's farthest away from the anomeric carbon that is chiral is, here's the anomeric carbon. Okay, here's this carbon, that's chiral. That's chiral. That's chiral. That's not chiral. This is the chiral carbon that's farthest away from the anomeric carbon. It's also the carbon whose OH initiates the intramolecular nucleophilic attack. This carbon determines stereochemistry, and it is on the OH in the Fischer projection is on the right in the Fischer projection, and that means it's D-fructose. D-fructose. After nucleophilic attack, the OH group can either be above or below the plane of the Haworth projection ring. Here I've drawn it below the Haworth projection ring. And so it is alpha fructose based upon the alpha anomer, but also it is D-fructose by virtue of the OH being on the right-hand side in the Fischer projection on the carbon that determines stereochemistry, or looking at it in the Haworth projection, the substituent that's attached to the carbon that determines stereochemistry, that's CH2OH, is above the ring in the Haworth projection. Okay, so what determines D or L in the Fischer projection is different than what determines D or L in the Haworth projection. In the Haworth projection for the ketose fructose as well as the aldose glucose, we're looking at the CH2OH. Likewise, if I were to put the L-alpha fructose form, okay, it's going to look like this. Here is our 5-membered ring, and carbon number 1 stays the same. Carbon number 2 is our anomeric carbon. I'll put the OH below the plane of the ring, making it the alpha anomer. Okay, everything else stays the same, except on carbon number 5, where I'll have the CH2OH below the plane, and I'll have the OH above the plane. Okay. Fill out the rest of these with hydrogens. So if I were to do a side-by-side comparison in the Haworth projections, these are Haworth projections. You can see what I've drawn on the right-hand side. This is still the alpha anomer, because the OH, after an intramolecular nucleophilic attack, decided to be at the bottom of the ring. It could just as well be at the top, but I've drawn it at the bottom or below the plane of the ring. So that makes this still the alpha anomer. But stereochemistry is going to be determined by the carbon farthest away from the anomeric carbon, and that's going to be carbon number 5. The CH2OH is below the plane of the ring, so this is D-alpha fructose. Okay, like that I could have a D-beta fructose. I can have an L-alpha fructose. I can have an L-beta fructose. I can have a D-alpha fructose, which I've drawn. I could have a D-beta fructose. What will that look like? The OH will be above the plane of the ring. I can have an L-beta fructose. Okay, I can have an L-alpha fructose. Okay, so I have different combinations of fructose. Okay, and that also works for all the other ketose sugars, okay? Not just fructose. Fructose is just one example of a ketose sugar. There are several other examples of ketose sugars. For example, sorbose, tagatose, cyclose. Okay, those are all ketose sugars. All right, so just as before, you can have an alpha or beta anomer, okay, and the anomer is determined by the anomeric carbon. So let me draw for you the beta anomer of fructose. So alpha anomer of fructose and the beta anomer of fructose. Okay, so the beta anomer would be that OH group above the plane of the ring on the anomeric carbon. So you see the OH substituent on the anomeric carbon determines whether it's alpha or beta. And here, carbon number 5 determines stereochemistry. I'll have it in the D form. That carbon number 5 has a CH2OH attached to it. And now what I've drawn is the beta anomer of fructose. Beta, because after intramolecular nucleophilic attack, the OH has decided to go above the plane in the Haworth projection. So when you have an intramolecular attack, when this number 5 carbon, that OH attacks, and then this pair of electrons goes to the oxygen, picks up a hydrogen, that OH is above or below. Okay, it can go in either one or two orientations. Okay. Furthermore, this is not a chiral carbon. After intramolecular intramolecular cyclization, now you have a chiral carbon. That is the quintessential definition of an anomer. Okay, now carbon number 2 has become chiral carbon at C2. That is basically what a chiral carbon looks like. So the OH can be below, that's alpha. The OH can be above, that's beta. There are two anomers of fructose, alpha and beta. So what happens when we join sugars together? One example is lactose, which is a disaccharide of galactose and glucose. That galactose, its anomeric carbon forms a glycosidic bond. So what is the anomeric carbon in galactose? Okay, well, if I told you that galactose is an aldose, okay, it is a C4 epimer of glucose. And if I told you, you should know that it's a C6 carbon. But if you didn't know, and if I told you it was a C6 carbon, that it was a hexose, you should immediately recognize that carbon number 1 is the anomeric carbon. So the anomeric carbon in galactose, more specifically the beta anomer of galactose, it's carbon number 1, that is the anomeric carbon, forms a bond with carbon number 4 of glucose. Glucose also is a C6 sugar. What is the anomeric carbon in glucose? Well, it's an aldose, and just like galactose, it too will have an anomeric carbon at C1. Okay, so notice, let me redraw this here as galactose with a beta 1,4 glycosidic bond with glucose. The beta represents the anomer of galactose that has formed a bond with carbon number 4 of glucose. Okay. Now, what is the anomeric carbon in glucose? Well, that's carbon 1. Is the anomeric carbon available at one end of the glucose molecule? The answer is yes. Okay, so if I were to draw the structure of lactose, which is nothing more than galactose and glucose coming together, forming a bond. It's actually a disaccharide, so it's just two sugars. All right, it's not a polymer. It is a disaccharide. So what is the Haworth projection for galactose? Remember, it is a C4 epimer of glucose. So a C4 epimer of glucose would be glucose, except the orientation across C, carbon number 4, is going to be different. So that is what galactose will look like. 1, 2, 3, 4. Okay. That is what galactose looks like. All right. This is its anomeric carbon. Okay. And it's going to form the beta anomer. Okay, not the alpha. The beta form, so that's the form where the OH is above the plane of the ring, remember, is going to form a bond. We call that a glycosidic bond, by the way. Going to form a bond with carbon number 4 of glucose. Okay, so let me draw glucose. 1, 2, 3, 4. So here is our bond. Okay. with glucose. Now that glucose could either be in the alpha form or the beta form, okay? Because that is its alpha carbon. I'll write it as the beta form, okay? Everything else stays the same. Here I've written glucose as the beta form, but it could just as well be the alpha form, or the beta anomer is the right way to put it. Okay, so that is lactose. Okay, we have galactose. Its anomeric carbon has formed a bond with the carbon number 4 of glucose. Okay, so couple of things here. I've labeled the anomeric carbon with a purple dot. This anomeric carbon, that purple dot on glucose, does not form a bond in this disaccharide. So that anomeric carbon actually is free to interconvert at its anomer and at its anomeric carbon. It's free to convert, and that hydroxyl group can actually be in an equilibrium with its aldehyde form. Okay, so if I were to just draw that as it is, and then here is our glycosidic bond. Here is our CH2OH. Okay, here is our anomeric oxygen. Now, let me show you what happens here. This pair of electrons that is on the oxygen can form a double bond, and this hydrogen leaves. So you have a free aldehyde that is in an equilibrium with the straight chain form. Okay. So now I understand that the free aldehyde is very, very rare. Okay, probably 1% the linear open chain form, but that is enough to react. Okay, so this can undergo aldehyde chemistry. All right, so one of the things it can do is that it could react with copper plus, it could react with iron, I think it's iron plus 2. It can react with some reagents, okay, most commonly Tollin's reagent. I believe that has silver in it, but I'm not entirely sure. This free aldehyde, even though it's 1% or so in population, it's not majority, maybe even less than 1%, that aldehyde is still available to do some chemistry. So that free aldehyde resulting from that free anomeric carbon that is not in a glycosidic bond, we call that available for reducing or for reduction. So lactose actually is what we call a reducing sugar. A reducing sugar. Fructose is also a disaccharide, but it actually consists of glucose with fructose. And the bond is a 1,2 glycosidic bond. The alpha carbon, the alpha anomer of glucose. So what's the alpha anomer of glucose mean? What makes the bond? Okay, the anomeric carbon makes a bond, so it's alpha 1, that's the anomeric carbon in glucose, makes a glycosidic bond with beta 2 of fructose. What is the anomeric carbon in fructose? It's carbon 2. So the glycosidic bond actually is formed by 2 anomeric carbons. So this is a carbon-carbon bond. I'm sorry, a carbon-oxygen-carbon bond, but the source of the carbons is the anomeric carbon. So here we have two anomeric carbons making a chemical bond or glycosidic bond. Okay, that's not what you saw in lactose. So let's draw the structure of sucrose. Okay, first we'll draw glucose. What form of glucose is it? The alpha form. Okay, so the alpha form means that the OH is below the plane of the ring. Okay, I'm going to draw the D form. Okay, the D form. So the D form would be that CHOH is up above the plane in the Haworth projection. Here is glucose. Okay, so alpha. Here is my anomeric carbon. It's the alpha form, so that OH is below the plane of the ring. But that's going to form a glycosidic bond with fructose. And it's going to form a bond with carbon number 2 of fructose in the beta form. So what is the beta form of fructose? Okay, in the beta form of fructose, okay, so here is the oxygen, here is carbon number 2, here is carbon number 1. Okay, here is that bond. Okay. This is the anomeric carbon. Carbon number 1 of fructose. Carbon number 2 is the anomeric carbon. Let's continue with carbon 3, carbon 4, and then this is carbon 5, this is carbon 6. Okay, I'll probably put this 1, 2, 3, 4, 5. I'll have, it really doesn't matter, I'll have the CH2OH below the plane of the ring. So this is technically the L form of fructose, but we're not going to concern ourselves with D or L. We're just going to concern ourselves with the glycosidic bond here. Okay, so here is our glycosidic bond. Now, if you see here, the anomeric carbon of glucose has formed an anomeric carbon with formed a bond with the anomeric carbon of fructose. Here's your glycosidic bond. There is no reducing end. Okay, this primary alcohol, the CH2OH, cannot form any other functional group. Okay, so this is very stable. Those electrons, those two lone pairs on the oxygen, they don't shift. Okay, they can't shift anywhere. They can shift on, if you look at and compare the structure with lactose, they can actually shift to form the free aldehyde. Okay, that's actually shown here. Okay, so you see here, this pair of electrons can actually go here and make the free aldehyde form. All right. That's a result of the COH bond on the anomeric carbon. Here on carbon number 5, this end of the molecule, this OH cannot form any type of alternative functional group. Primary alcohols are just what they are, a primary alcohol. All right. So there is no reducing end to this molecule. We call this a non-reducing sugar. A non-reducing sugar. Another way you can tell it's a non-reducing sugar, there's no reactivity at this end. This will be non-reactive to Tollin's reagent or copper ion or ferrous ion or Felling's reagent, it will be non-reactive because the anomeric carbon, the carbon that undergoes a hemiacetal intermediate or a hemiketal intermediate, those two carbons are bound up in a glycosidic bond. And so notice here, one final thing before I go, is that we designate the glycosidic bond if the anomeric carbon makes that bond. If it is involved in the glycosidic bond, we have to designate that as an alpha or beta. All right, so other things such as a beta 1,3, well, beta means that the anomeric carbon in carbon 1 is forming the glycosidic bond with carbon 3. Now, unless that carbon 3 is the anomeric carbon, we can just say beta 1,3. Or in this case with lactose, we can go with beta 1,4. Okay? With sucrose, since both anomeric carbons are involved in the glycosidic bond, we have to designate both atoms as whether they are alpha or beta. So sucrose is a disaccharide of glucose in an alpha 1 beta 2 glycosidic bond with fructose. Okay. Alpha 1 beta 2 glycosidic bond is sucrose. It's a disaccharide just like lactose. It's a disaccharide just like lactose, but we have to designate alpha 1 beta 2, whereas, because the two anomeric carbons are making the bond, right? Whereas in lactose, it's just beta 1,4 because only the anomeric carbon of galactose is involved in the glycosidic bond. More specifically, it's the beta form. Okay, so beta 1,4 because the beta anomer of galactose is making a bond. Alpha 1 beta 2 for sucrose because the alpha anomer of glucose is making a glycosidic bond with the beta anomer of fructose. All right, alpha 1 beta 2 sucrose, just simply beta 1,4 for lactose because again it's the beta form of galactose forming a glycosidic bond with carbon number 4 of glucose. Carbon number 4 is nothing. Okay, it's not the anomeric carbon. Okay, carbon number 4 really doesn't determine whether it's an alpha or beta anomer. It's carbon number 1 if it's an aldose, it's carbon number 2 if it's a ketose.